That's quite a good morning. Okay, so this we have 1.5 hours to talk about Floquet systems. Okay, I will mainly cover topological Floquet systems to go along with the theme of the school. So this is going to be, I guess, divided in 3 parts. I'll first tell you about the basic idea of Floquet theory. Then this resembles in some sense intuition from band theory that we have. So we will, in the second part, look at the differences between Floquet and driven systems.
Sorry.
I'll try. Let's go for blue. Floquet and equilibrium. Is that better or?
Yeah, better.
Is it good enough?
Yeah, it's just a reflection as well.
I don't know. Should I write bigger? Should you come forward?
Bigger.
Okay, equilibrium system. Okay, the important things I'll write big. And lastly, I'll show you some slides about experiments on these kind of systems. Okay, so what is it, a Floquet system, first of all? So for the last couple of days, you've been, I think, exclusively hearing about undriven equilibrium systems. So you've been implicit, so either you've been talking about band structures, which you can populate thermally, of course, or you've been implicitly thinking about 0 temperature ground states of materials and they have a gap or something, and then you're really thinking about equilibrium properties. Now for the next 1.5 hours, we are talking about systems which are time dependent, where the Hamiltonian depends on time, okay? And this becomes a Floquet problem if the Hamiltonian depends on time with a period omega, with a period t, or a frequency omega 2 pi over t. So a periodically driven system. So h of t plus capital T is the same as h of t. Okay. So this is the type of system that we want to study. And we would like to look at these systems most of the time, except for a small comment that I'll make, as a closed system in terms of particle exchange. So we don't think about coupling that now this thing also gives up. Thank you. Maybe I should ditch those. So we don't want to think about coupling the system to a bath, but look at the system in an isolated way. Okay, so yeah, this one is the best. Okay, cool. And this one's also good. This one is semi-okay. So what could be a problem if you think about such a system that's isolated and I drive it in a time-dependent fashion? So for example, like you should think about, for example, in a condensed matter setup, taking a piece of material and irradiating it with light, which is shine light on it and you see what happens. Or another example is that you take a crystal and you coherently drive phonon modes in the crystalline, so start to shake it. Another example that's quite, where this kind of theory is often applied is in cold atom systems, where often you couple lasers to a lattice of ultra-cold atoms and you start to shake them or do something like that. So what could happen generically? What could be a problem? Well, obviously this, yeah.
Well, you put energy in, right? So you can get like catastrophes.
Yeah, exactly. So you're going to heat that system up, right? Eventually it's going to sort of generically, this is going to just go to infinite temperature and boom, right? Okay, so that's one of the issues that we'll be thinking about later on. Okay, so let's start to think about limits in which we can already say something about a driven system. So one limit you have actually used already, I think, as a thought experiment in the last couple of days when you were thinking about adiabatic connection of Hamiltonians. So suppose I have an energy gap in my system and my frequency is much smaller than this energy gap. Then what will happen is that as you drive the system, the Hamiltonian or the ground state, if you start off in a gap ground state, will actually smoothly follow the instantaneous ground state of the Hamiltonian. So this is the adiabatic limit. And another limit that so this is a gap energy. Another limit that you can think about is if you have a finite system and it has a maximum of the energies of the eigenstates, and you drive it very, very fast, then you could think that since there is no natural energy scale that's in the system that is sort of the same order as this huge driving energy, then you could think that maybe you can make some approximations that would make the system look like a quasi-static system, and the system sees this fast driving only as some sort of background that changes its properties a little bit. So another limit which is convenient to think about is if you have a frequency that's much larger than the system energy scales, and then we can sort of do something that we call high frequency or Magnus expansion. Okay. What could be a problem if I think about a crystal or a thermodynamically large system? What could be a problem with this one? If this is an interacting system, then there is no upper limit. If in a thermodynamically large system, there is no upper limit to the energies. I can always populate, of course there is a ground state, but then when you start to think like what the energies you can construct, you can always put your particles in very high energy states, and if you have exponential, thermodynamically many of them, there's just no upper end to that. Okay, so this makes sense only in either a finite interacting system or in a non-interacting system where effectively you only think about single particle physics and then you have a bandwidth. Okay, but now let's think about what we can actually do, in describing these systems. Of course, we'll discuss in a bit of detail this high frequency expansion, but also we'll look into systems which are not in either of these two limits. Okay. So how are we going to describe them? Obviously, the energy is not conserved, so it doesn't make sense to think all that much about the Hamiltonian as itself. And the object of interest then is not the Hamiltonian, but the unitary that describes the evolution of the system. So we are interested really in this object, u of t, that describes the system evolution. And of course, we can solve the Schrödinger equation for it, and we get something like this. Let's say, start from 0, integrate to some time t, h of t, dt. Okay, so this is a time-ordered exponential. If you are a bit scared of this calligraphic t, you can also always think about, approximating this maybe numerically or so as just a product over exponentials I, and then you take the instantaneous h of t at some ti, say, and then the product, the difference ti plus 1 minus ti. And this is ti from 0 to t, right? So you can discretize your time, make the fine spacing, and then multiply these matrices. You get the approximation to this u of t. Okay. So now, typically in such a Floquet system, we are, this u of t, of course, it's varying within, or it's describing the full evolution within a period and between the periods of the drive. But to simplify matters, we could just look at stroboscopic evolution of the system. So we can say, well, let's actually only look at times which are integer multiples of our driving period. So let's look at u of n times t, and due to the periodicity of the Hamiltonian, this is u of t to the power n. So if we are only interested in the system at integer multiples of this period, then it's just enough to look at u of t, u of capital T. Okay, so this is what's often called the Floquet unitary then, and now we thinking of unitaries, we often make a convenient change in notation. Instead of describing the system by this unitary, we go to a formulation in terms of a Hermitian matrix that we call HF, and multiply this by t. So we represent this as an exponential of a Hermitian matrix. And this Hermitian matrix is called the Floquet Hamiltonian. So obviously, this matrix or this operator always exists, right? I mean, I can always rewrite a unitary as the exponential of a Hermitian matrix, but there is one catch here. We should not think of that as a Hamiltonian of a real physical system necessarily. In particular, this thing may not be local. So in general, this is not the local operator for a generic system. Okay, there are situations where it is, though. So this, however, is now the main object of interest. So we would like to know how to compute this Floquet unitary for a specific system, for example, in this limit of high frequencies. But let's, before we do that, let's just make sure we understand well what this mapping here implies. So if we have this Hamiltonian, well, what we usually do is we try to solve it, right? So let's say we have a spectral decomposition of this Hamiltonian, which looks like we have a sum over eigenenergies lambda and then these eigenstates. Then obviously the unitary has also this decomposition, e to the I or minus I e lambda t, and then the same eigenstates. But now there is an issue, right? We said what is physical really is this unitary, not so much the Hamiltonian itself. So what is physical is not the eigenenergy here, but the exponential of this eigenenergy. So this is physical. Okay? So what that implies is that E lambda and E lambda plus 2 pi omega is the same thing. Sorry, but plus omega. Okay. So we should identify these energies. They're physically the same thing. What obvious problem follows from that? If we think about this as a Hamiltonian, we solve its spectrum. Typically, we think about a ground state energy. We think about occupying states. Like when we have fermions, we are occupying a Fermi sea and stuff like that. Here, there is no notion of ground state anymore. I can always add any, actually integer multiple of any frequency, And I can go basically, as deep or as high up in energy as I want, and I have the same eigenstates. So how am I gonna, if I think about a fermionic system, how am I gonna populate these states? What is a ground state? What's the notion of a ground state? All this, that's the upshot, is essentially gone. You can basically sort of abandon this notation. There is no Fermi sea. There is no ordering no natural ordering of the energies. Because it's not it's not a local quantity, right? I mean, it's of course certainly an operator that describes an exponentiator, describes the evolution of the system, but I should not think of it as an effective Hamiltonian of a physical system, because that effective Hamiltonian could be non-local and physical Hamiltonians should be local. And this comes, of course, because we are integrating, right? When you start to do such an integral, of course, each of these terms is local, but they don't necessarily commute when you take the product here. Each of these factors don't commute, and then you're agglomerating. If you want to evaluate that in some perturbative way, say you're agglomerating longer and longer commutators, and then you get like long-range terms essentially. Yes, yeah. I mean, this is completely generic. I mean, for a time, yes. So this is not necessarily a property of a Floquet system, but our desire to write it, to just look at this particular unitary and write it as the exponential of a time-independent. This is time-independent. Maybe I should have stretched, right? As the exponential of one Hermitian operator. That's only reasonable to do or to even attempt in a system where it's periodic. Otherwise, we anyway want to look at any time, not just as stroboscopic times. Yeah. Okay, so I think it's high time to think about an example where we could, so the question is now basically, if I have my h of t, right, how do I get the Floquet Hamiltonian in some controlled way? Okay, and okay, so I said there is this high frequency expansion. And so let's say our original Hamiltonian h of t is decomposed into Fourier modes. So I'll call this HL e to the minus I omega L t, and I sum over L. Okay. Then I could hope that I can actually find in a perturbative fashion this Floquet Hamiltonian as a sum of terms that I'll call HF upstairs n. And this n goes from 0 to infinity. And I want that the nth term in my expansion is proportional to omega to the minus n. Okay, or omega, I mean, some natural energy scale in the systems, or the norm of maybe these Hamiltonian, to the inverse nth power of the frequency. So if the frequency is large, this thing will somehow converge, or I could hope, right? So, now this deducing these terms one by one is not that, I mean, there is a systematic way of doing this, and the zeroth term is simply just the integral from 0 to t dt h of t. So it's just the average of this Hamiltonian over one period, and that's in this expansion is equal to h naught. And then let me also give you the first term. That's 1 over omega. So the first term in this, the first non-trivial term in this expansion. And this is sum over L equal to 1 to infinity, 1 over L. And then comes the commutator of the term with the Lth order term with the minus L term in this expansion. Okay, so you can derive this, just basically using this formula and doing perturbation theory in omega. So you can go on, find this in the literature if you want, all these expansions. So let's do an example where we can use this formula, okay? And the example, I was already saying that a lot of interest in Floquet theory comes from systems which are driven by shining light on them. So you heard a lot about graphene yesterday, so maybe it's good to look what happens when we shine light on graphene. And to make things interesting, we are not looking at linearly polarized light, but at circularly polarized light. Okay, so so the Hamiltonian that we would like to study is h of t is some overall velocity. Then we have kx sigma x plus ky. Sorry, what did I want to do? Ky sigma y. And to account for the light field, we minimally couple it to the electromagnetic gauge field. So there is an ax of t. Here comes now the time dependence, and an ay of t. And what would be circularly polarized light? Well, it's just, we think about a homogeneous exposition to some light. So there is no spatial dependence in this. We don't need to use the gauge field of spatial dependence in this A field, but we could simply say A is some overall amplitude times, what did I choose here? Sine omega t, and then cosine omega t for the y component and 0 for the z component. So this is rotating in the plane, so there is a pi half phase shift between the x and y component, circularly polarized. Okay, so let's apply our formulas and derive the Floquet Hamiltonian. So the zeroth, so what's the zeroth order? HF of 0. Sorry? Exactly. That's our old Dirac, the one that we know and love. Kx sigma x plus ky sigma y. Very good. Now h1 of f is a little more tricky. Sorry? That's, yeah, oh, sorry, maybe this is a very squashed 0. Okay. Well, for that we might need to look at what is the expansion of the h of t. So clearly h1 is v, let's say, minus va2, and then something like this. Can you still see when I write down here? Not so really, right? Okay, let me write it up there. Okay. So anyways, h1 is minus va over 2, like that, and then minus 1 is like that, right? So now you see that there's important sign change here due to the circular polarization. And to get the first order correction to this Floquet Hamiltonian, we just need to take the commutator of the two. So, so let me write the Floquet Hamiltonian as, again, v kx sigma x plus ky sigma y plus, and now comes the commutator of these two guys. And if you get your factors of 2 right, you should get a squared v squared over omega. The omega comes from this part of the formula. And then which matrix would I have to put here? Excellent. Okay, plus other stuff, so a over omega squared, I guess. Okay, so this is sort of our expansion, our perturbative result. So what is this? What is this physically? Oh, sigma at z, right? Who's very good. That's the mass term, that's right. Very good. So what does the mass term do physically? If you just have, let's say we think about, now of course what I didn't really take into account so far is that graphene has two valleys, right? So this is like just one valley, but what does it do for that one valley? So think about, you've heard about Chern numbers and stuff like that yesterday. It moves the Dirac point. So yesterday we had a Weyl point, right? That was a sigma z times kz. That would be moved by whatever this was. But now we don't have that, so it doesn't move. It opens a gap, right? Yeah, that I think somebody already said that before. So this gap. So if I was to integrate the Berry curvature, or if I looked at the Berry curvature that's created by this gap, and I integrated it over all of space, having just this Hamiltonian, does anyone know what the result would be? Right. Excellent. So this is like a single Dirac electron. So if I integrate the Berry curvature, I don't know, something like this, dk over all dk squared. And of course, there's only the 1,2 component. I would get 1/2. So that usually this would be the formula for the Chern number. If there was a periodic system, you would have to get an integer. Yeah. Okay. Now you get 1/2. That 1/2 can be there because we have not applied periodic boundary conditions here. If we look at the spinner at infinity for this system, it actually winds once around and you cannot compactify that space because it winds, right? It's the winding that Andre talked about that appeared either at the south or the north pole. Okay, good. So now we have another valley in graphene, and we can already think about what would happen at that other valley. So there is basically two options. So we're talking about spinless graphene here, right? This sigma is not the spin, but this is the sublattice degree of freedom, right? Of course, the light doesn't interact with the spin. We don't talk about spin-orbit coupling or anything of that here, of that sort. So, so in spinless graphene, there are only two mass terms that you can put. One mass term breaks inversion symmetry. This is staggered sublattice mass. So if I give a different mass, different energy to these two sublattices. And the other mass is the one, the Haldane mass, say it's called, is the one that breaks time reversal symmetry. Obviously, what we've done here is we've broken time reversal symmetry with our circularly polarized light. So, and the difference between the two masses is the sign of this term relative between the two Dirac points. So for the staggered sublattice mass, you get plus 1/2 here and minus 1/2 in the other valley. But so this is the sublattice potential, and if you have the Haldane mass, then you get plus 1/2 and plus 1/2. Okay, and of course, so since we are breaking time reversal symmetry here, what will happen is the second case, the other valley will get basically a mass of the same sign, or this Chern number will give you the other 1/2, right? So the Chern number will be 1/2 plus 1/2. Okay. So equal to 1 for this graphene thing when you add up the two valleys, when you drive it with circularly polarized light. Another option is to think about driving the surface states of a three-dimensional topological insulator, which have the same lower energy Hamiltonian, and then you open also a gap. There you can actually have this half integer quantum Hall effect, if you wish. This half integer quote-unquote Chern number, because you don't need to compactify. I mean, because this system is not defined in 2D, but just the surface of the 3D system. Okay, fine. So this we understood, maybe. The whole conductivity is of this system is, in this driven case, is going to be 1. Graphene becomes a Chern insulator when driven with circularly polarized light. Of course, since there's also spin, it's actually going to be 1 plus 1 for each spin species. Now there is something cool about this one. So this was to demonstrate how this expansion works. But actually, in this particular case of Dirac electrons, we can even solve the problem exactly. And that's of course very nice. So let's look at this Hamiltonian at k equal to 0 and any given time. Then it will look like that. Okay. So this looks interesting, not so complicated. And let me propose something. Let's use a unitary rotation of the basis states that depends on time, like this. Do you see what would happen if I take this Hamiltonian and apply this unitary? Okay, sigma z, right? This is a diagonal matrix. I mean, you know what that would be, right? This is e to the I omega t over 2. Right, that. So what's the result? I'll do the VA. The rest is on you. Okay. Come on. I mean, it's like not so hard, right? You see that this guy goes on this row, and that guy goes on the other one. So they will actually conspire in such a way that you get rid of this time dependence. So the I stays. Okay, fine. So this now is completely time-independent matrix, completely time-independent transformed Hamiltonian of the system. So what I did is I was going into a rotating frame, and I exactly removed the time dependence. That's a very special property of this particular system. There are not that many where you can do this, or this particular drive of the system. So there is a little, so this is not yet the effective Hamiltonian for the system, because I should also remember that when I have the Schrödinger equation, right, and I'm doing a time-dependent unitary transformation on the system, there is a contribution coming from the derivative. So when I have, say, I, and then, okay, let's multiply it from the left with this W, and the transformed states that I want to look at are W psi, then my transformed Hamiltonian is this guy, and then again W psi. Then when I want to bring this into the form of I partial t acting on W psi, then I need to take care of this action of t on that W, right, which is time dependent. So I have to put that on the other side. So now I have partial t W dagger. So this only acts on the W, and then that, right? So actually my effective Hamiltonian is gonna have this extra contribution, and so in total, it looks like, let me call this HF tilde. That was the part that we already have. And then that second part basically pulls down this sigma z term, and you get rid of the I. So that would be our exact Hamiltonian in the time-independent gauge, if you wish, or the time-independent frame, in the rotating frame. So let's compare what we got before with this exact result. So obviously, so this was only at k equal to 0, right? So this will only tell us about the gap. Now, so the gap of this thing is going to be 2 times VA squared, sorry, is that the 1/2? I think this 1/2 doesn't count. Yeah, there's no half there. VA squared omega over 2 squared. So this 2 just because I want the gap, okay? So the eigenvalues would be plus minus that thing. Okay, if we expand this, then there is something that is the lowest order is going to be omega. If we expand it in small a, right? Plus order a over omega squared. That doesn't exactly look like the gap that we got here, right? It's not, that gap is going to be V2, so the gap here is 2V squared A squared over omega. What's the catch? The catch is still on the board. You can spot it. Exactly. These bands, so this is really like just reminding us that these bands are only defined modulo omega here. So that difference is really not important at all. The band structure of this Hamiltonian is going to be like that. That thing is going to be omega plus this, V squared alpha A squared over omega term. But each of these bands is repeated for every omega. And so on, right? This keeps going like that forever. And so what we've computed here is simply the splitting. So this difference, this repetition here is omega, okay? And what we've just computed here is the small splitting between the two bands that are hybridizing here, okay? So it's all good. Just reminding us that there is this ambiguity in omega when we define energies in Floquet space. Okay, so this is enough, I think, to give you a feeling how we derive effective Hamiltonians. Of course, here I cheated a bit because I chose a system where we can do things exactly. In general, you'd have to suffer through this if you have some high-frequency expansion that you can do. And so I think I'd like to go to the second part. If there's questions, then we should take questions at this point.
So only one period in energy is really physical?
No, they are all, in principle, they are all the same. Oh, you mean like, two? No. Okay, this repeats forever. This is just sort of, it happened to be that guy, but I could have actually chosen, I guess, I'm wondering whether I could have chosen a different frequency here. No, probably not. I don't know. Yeah, no. They're all, I mean, this is like a gauge transformation that brings you from one to the other. So, yes, in principle, yes. I mean, physically, of course, this will include, so if you think, so this is math, right? If you think about physically now driving a system, of course, the more you want to go away from the actual energy or the natural sort of gauge that you would pick, the higher order processes you would need in your drive. So if this driving amplitude is small, then say if you think about the occupation of these bands in the Floquet space, then to lowest order, you'll try to stay near where you started from. But there's nothing that prevents you to go to any of these states.
Another question, is it always easy to tell, so these bands overlap, so is it always easy to tell which is the zeroth period? In principle, this is not, I think it's not a well-defined question, right? Because they are gauge equivalent, they're just gauge equivalent, yeah. Yeah, no, it doesn't. Actually, that's a good question. It doesn't. Why does it not? Because the linear polarization, you would say, okay, let's come with, so the linear polarization doesn't have that pi phase shift, right?
And then what happens is that these two, I mean, the fact that we got a gap here is because these two anti-commute, they do not commute, right? We get sigma x times sigma y, and we have this relative pi phase shift, so that the two, I mean, if you actually compute this commutator, you get two contributions, right, that add up because of that relative minus sign. And if you didn't have that, then there would be nothing. So there's no gap in a linear polarized system. And we'll actually, I'll show you the experiments later. We can have a look and see that. Okay. Okay, let's do now two differences. I mean, I've already highlighted some differences, but still we are sort of thinking this looks like a band structure. We're talking about Chern numbers, so maybe we can carry over a lot of the intuition that we have from non-interacting equilibrium bands to Floquet systems. And